Hey everyone, welcome back. We're going to move into the trig equations now, part of the Precal review. Before we actually start with these 17 million examples, I want to show you a resource that's on my website for you. It's called the trig cheat sheet. You can go to my website and print one out yourself. It's a nice little handy reference for you, so that way whenever you're working through these questions, if you forget some of those trig identities or rules or properties, you have it all for you in one nice convenient spot. A lot of the stuff you should probably know, like everything up here in the top left and the top right. Hopefully that's pretty ingrained in your brain by now. The domain and the range and the period. If you have a general idea about what the graphs look like, I think all that should be pretty okay. It's not terribly important. The formulas and the identities, if you remember back to Precal, there's like a lot of them. You don't need to know every single one. You should know these general basic ones. You don't really need the even and odd that often. Don't really need to convert between degrees to radians. Don't really need the cofunctions or the periodic. But you really should know all of these. They're pretty basic and fundamental. You should also remember inverse trig and what that means. Again, we'll deal with the inverse trig later on towards the end of the year, but it's there for you. Definitely should know what tangent and cotangent and what all the reciprocal functions are. And then on the next page, you see I have circled and starred the Pythagorean identities and the double angle formulas. Those are the ones that you really need to know. All the other ones don't really come up very often. If you're in Calculus BC, you'll see these come up in the second semester, and also maybe a little bit of the half angles. But for your general Calculus 1 or Calculus AB course, we don't really need to know those. We don't really need to know those. And then we never really ever need to need these at all. So it's kind of nice. There's lots of those trig identities. Some kind of scary thinking back to Precal and how much time and energy you spent going through them. But really, the Pythagoreans and the double angles are the ones you should focus on the most. So if you know those, great. If you don't, you probably should. Right? Pythagorean identities, they're not too bad. A little bit of a review also, right? There's really just these three, the double angles and then the Pythagoreans. These three are the key to everything, and then from them you can kind of derive everything else that you need, right? We know for the cosine double angle, there's actually three different formulas. Don't bother with the tangent, it's not necessary. But for cosine 2 theta, you could have this, this, or this, right? But if you know the big one, which is just cosine squared minus sine squared, you can go ahead and get those other two pretty easily, and they just need a Pythagorean substitution. Speaking of which, let's kind of look through and go through the Pythagoreans really quickly. The most important one, obviously, is your sine squared plus cosine squared equals 1. Yes, you could flip the order for that, it doesn't matter. In order to get the other two big identities, take your original, and if I were to take this and I divide it by cosine squared, well, cosine squared divided by cosine squared would be 1. 1 divided by cosine squared would be secant squared. And then here, if you took sine squared and you divided it by cosine squared, you would get tangent, right? So from your main Pythagorean identity, you can get this other one by just dividing by cosine squared. And then kind of similarly, you can get this other one, but you would divide by sine squared. So sine squared divided by sine squared is 1. Cosine squared divided by sine squared would be cotangent squared. And then 1 divided by sine squared is your cosecant squared. And then you can also manipulate these a little bit. Like, let's go back here. I've got sine squared plus cosine squared equals 1. If I somehow needed to do a substitution, and I needed to get rid of the sine squared, that means you would have to get the sine squared by itself. So I'd have to take the cosine squared and subtract it over. So I know sine squared is equal to 1 minus cosine squared. Kind of the same thing if you needed to get rid of and make a substitution for a cosine squared. You would need to keep this on the left, but then move the sine squared over. So you see, from this main Pythagorean identity, you kind of have these two offshoots that come from just adding and subtracting stuff around. You rarely want the 1 by itself. Typically, you're going to want either the sine squared and then change it to 1 minus cosine squared, or you'd want the cosine squared, which you could change to 1 minus sine squared. You could do the same thing for the other two. Like here, if you look, tangent squared plus 1 equals secant squared. So if you had to get rid of a secant squared, you could change it to tangent squared plus 1. Or, if you needed to get rid of a tangent squared, you'd have to move the 1 over. So you'd have secant squared minus 1. If you also wanted to, you could get this third equation from this little offshoot. If you moved the tangent over, secant squared minus tangent squared. That's not really super helpful. Definitely you may need this, but the 1 equals secant squared minus tangent squared. Yeah, you wouldn't really ever want to change a 1 into all of this stuff. But if you ever saw a secant squared minus a tangent squared, that would be equal to 1, very much the same way that sine squared plus cosine squared is 1. There's two more. Let's go through and kind of get them from this last little offshoot. Here the cosecant is by itself, so you could also just subtract some stuff around. I could get the cotangent squared by itself, subtract the 1 over, and then you could get the 1 by itself, which is kind of rare that you want, but it's there. Right, so really there's 9 Pythagorean identities. There's the 3 big ones, right? There's the one kind of grandfather identity, and then from it you have the 2 other large equations. But then each one of these 3 large equations has 2 extra offshoots that you can get by just subtracting stuff around, depending on what you want to isolate. Right, so there's 9 Pythagorean identities, but if you remember this main one, and you remember the strategies for how you can get all the other ones, you hopefully can answer any question that you may potentially need. Right, and then going back to the double angles, you have the sine of 2 theta is 2 sine cosine. That one comes up fairly frequently, so you'd want to know it. And then the cosine double angle, there's really 3 of them, but kind of the same thing. If you know this main one, if you ever need to get the other 2, you could, right? So here, I'm taking this main one, and if I wanted to get rid of the sine squared, like sometimes you're working an equation and you only want to have cosines. So I could take this sine squared, and I could use a Pythagorean substitution. And instead of cosine squared minus sine squared, I could have cosine squared minus, and I'd do my Pythagorean substitution, right? Instead of the sine squared, 1 minus cosine squared. And then you could just distribute the negative, and you get this extra cosine double angle, which is there on your formula sheet for you. But how they got from this one to this one was you just do a Pythagorean substitution to get rid of the sine. Same thing here, except what they do is get rid of the cosine squared by doing the Pythagorean substitution. And there's the work I have for you, right? Cosine squared, get rid of it with the Pythagorean substitution minus the sine squared, and then you can just combine your like terms. So your double angles, you should know the sine double angle. You should know the main cosine double angle. From this, you could get the other 2, but if you know the main one, that's the most important. And then the Pythagorean, there's really 9 of them in total. There's the 3 kind of main ones, and then each of the 3 main ones has the 2 offshoots. But if you know the big one, and you know the strategies, you should be able to get the other 8 pretty easily. Right? So these 3, the 2 double angle and the main Pythagorean, those are really from Precal of the main things you need to know. Okay, and of course the unit circle. If you don't know the unit circle, I don't know what to tell you. Go back, study it. You really need to be familiar with the unit circle. All right, so now, with all that kind of said and done, let's actually get into some of these questions in the notes packet. I think I actually paid for my subscription to get updated, so I should, I believe, be able to go more than 15 minutes, but I guess we'll see when it cuts me off here in about 5.5, so hopefully it doesn't. Alright, sine of x equals 1/2. Notice we're not going to have to mess with plus 2k pi or any of that nonsense. We generally only care about your unit circle answers. So at the end of the question, we are only interested in the things that fall on my unit circle between 0 and 2 pi, which is nice. We don't typically deal with extra revolutions. But sine of x equals 1/2. Here it's pretty easy. Remember, sine's the y value. So you'd come over here to your unit circle, or you just draw a unit circle. I'll kind of do this. I know sine's the y value. 1/2 is the smaller number. So I know there's 2 points on the unit circle where the y value is a positive 1/2. And then I would just need to know that this is pi over 6 and that this is 5 pi over 6, right? That's where your unit circle knowledge comes in. A lot of the stuff that you see in the calculus class in regards to trig, it's usually the easier variety type of questions. Some of these trig equations can get pretty complicated. If you remember back to pre-AP Precal last year, some of them can get really nasty. You don't usually see the really hard ones in calculus. Usually they're of the easier variety. But if you don't know, hey, sine is the y value, 1/2 is that smaller number, so I'm looking at these 2 points on the unit circle, you're gonna be in a really rough spot this year. And then you need to know that those 2 points on the unit circle correspond to the 2 angles. And we really only care about the radians. It's rare that we do stuff with degrees, right? Radian for my class. So then here we're done, right? We have pi over 6, 5 pi over 6, done, right? That's the type of question that usually comes up. All these harder ones are a little bit rarer. Next one, cosine of x equals root 2 over 2. Again, unit circle values, really nice. So unit circle, that's a positive. The root 2 over 2 is the one where it's kind of that perfect 45-degree angle. Cosine is the x value, that's a positive. So you know you're going to have 2 points on the circle, and then you would need to know that that's pi over 4, and then that's 7 pi over 4. Right? It's not too hard if you know cosines x, sines y, and you know where the angles are around the unit circle. You should be pretty okay for the majority of the trig in my class. So here we got pi over 4. 7 pi over 4. Really nice. Right, next one's a little bit harder. We got tangents, which is a little bit annoying, and also you have to factor it. So let's see, I've got a tangent squared plus a root 3 tangent. You can factor out a tangent. And then what you would do is just set each factor equal to 0. So tangent of x equals 0. Set it equal to 0, and then move the root of 3 over. So I know tangent of x could be 0, or tangent of x could be the negative root of 3. For there, you're just going to want to go to your unit circle. Remember, tangent's y over x. Now let's go around to this unit circle. We'll write the tangent values in case you don't remember them from Precal. Cosine is the x value. Sine is the y value. Ooh, I'm kind of off the screen. Let me zoom out, see if that helps. And then tangent is your y over x. So here, y over x, tangent would be 0. Here you'd have 1/2 over root 3 over 2. What's really nice is that the 2's in the denominator are always going to cancel, right? I'll do this once for you, but otherwise I'm not going to. If you have 1/2 over root 3 over 2, y over x, those 2's are always going to end up canceling. And you'll get 1 over the root of 3, which, if you want to rationalize it, is root 3 over 3. Okay, here you'd have the root of 2 over the root of 2, so the tangent at that spot is 1. Here you're going to have the root of 3 over 1. So these numbers right here are the tangent values that I'm writing down. You can do kind of the scratch work for it if you want, but if you just remember top of the y over top of the x, that's how you can get the tangent values pretty quickly. Tangent here, if you have 1 divided by 0, you can't divide by 0. So the tangent there is undefined. And then because of the symmetry, you're going to start to see some of these similar numbers, except in this quadrant 2, they're going to be negative. Here the tangent, 0 over negative 1, that's 0. And same idea, 3 over 3, 1, root of 3. This one's undefined at the bottom. This one's your negative root of 3, negative 1, negative root 3 over 3. Right, so your tangent's a little bit harder, but you should be able to get them. Just remember, it's the y over the x, and the 2's in the denominator. They're always going to cancel. So let's go back to this question that we're actually working on. We want the angles where tangent is 0. There's 2 of them. And I want the angles where tangent is the negative root of 3, right? There's also 2 of those. So then you would just go to your unit circle. Here's the 2 angles where the tangent value is 0. And then you need the negative root of 3, so it looks like I'm up here and I'm down here. Right? So then you would just collect, and you're going to have 4 answers for this question. It doesn't really matter what order you want to write them in. I typically will just answer them by chunks. So for the tangent of 0, I would just pull those angles. You don't need the root of, you don't need 2 pi, because it's strictly x is less than 2 pi. If you were to put 2 pi, that's fine, but 2 pi is not really in the interval where we want the final answers. If you were to put it, I wouldn't take off points, but you don't need it. But those are all the angles where the tangent is 0, and then you still needed to go snag the other 2 angles where it was the root of 3, negative root of 3. So that one ends up having 4 answers. If you were to put the 2 pi, then you could potentially have 5, but you don't want the 2 pi because it's non-inclusive. Ooh, looks good. Over 15 minutes and it's still working. That's very wonderful. All right, let's keep going. Cosecant of x minus 2 equals 0. Add the 2 over. Now, I don't really want to work with cosecants. I like working with sines and cosines, and if push comes to shove, I guess I can work with tangents. Here, instead of the cosecant being 2, I'm just going to go ahead and do the reciprocal. So the sine of x is going to end up being 1/2, and look at that. It's literally the same exact question that we did on example A, right? I'm not going to redo it. I'm just going to copy those answers. But remember, you'd be looking at, okay, the y value is 1/2, so that's those 2 points on the unit circle, and you'd have to know what those corresponding angles are. So if you ever see a cosecant or a cotangent, once you get that term isolated, right, don't do the reciprocal yet, because you've got this minus 2 on the same side as the trig. But once you isolate the trig, then you could do the reciprocal. But remember, if you do the reciprocal of the trig, you also have to do the reciprocal of the constant, right? So cosecants and secants and cotangents, really, you don't want to work with those, so you use some of your identities to avoid them. All right, next 2, a little bit harder, but that's okay. Again, most of the trig stuff you're going to see in my class will be like these 4 questions, where they're not super complicated most of the time. Probably like 90% you're going to see stuff like A and B. Occasionally, maybe you have to factor a little bit, or maybe you have a tangent, or occasionally maybe you have a cosecant or a cotangent. But there's not usually going to be stuff like these next couple of examples. But it's important that you know how to do them on the off chance that something does show up. All right, so this next one, you're going to factor, right? And if you need to, you could think about it. Let me get a piece of scratch paper. If you need to, you could think about it in terms of just like x's. Like if you had 2x squared minus 9x minus 5 equals 0, right? Here I've got 2 cosine squared minus 9 cosine minus 5, right? So this is the same thing, but here my cosine, or my x, is representing my cosine. But if it put it into x's, it usually helps students see how you can factor it a little bit easier, right? Now this is all kind of extra. You don't have to do this. If you can factor it while it's in cosines, that's all well and good, and I hope we can all get to that point. But if you need to switch it over to x's so you can see how it factors, that's perfectly fine. I believe this one is going to factor 2x plus 1 and then x minus 5. And remember, you always check your factoring by just multiplying it back together. So 2x times x, that's going to give you 2x squared. That here would give you a negative 10x. Then that would be a plus 1. Negative 10 plus 1 does combine to give you the correct middle term. That's really nice. And then those two give you that, right? So very good. I know how to factor it. But remember, I didn't have 2x squared minus 9x minus 5. I had cosines instead of x's. But the factorization is still the same. So going back to this example, we're going to have 2, and then instead of x plus 1, we're going to have 2 cosine of x plus 1, right? This type of the formula is going to be the same thing as when you factor it with the cosines, but instead of the x, you go back to the cosine. And instead of x minus 5, here you'll have cosine of x minus 5. Oh, come on, pencil, you can do it. Okay, so just be cognizant of that. If you need to switch it over to x's to help you factor, that's perfectly fine. Just remember, you're not really dealing with that with just x's. You need to switch it back to cosines. Okay, next you would just set each factor equal to 0 and then solve it. So here we have cosine of x is equal to negative 1/2. And here you'll have cosine of x is equal to 5. You just set this equal to 0, add the constant over. Or here you'd set this equal to 0, subtract the 1, divide by 2, right? I kind of just skipped that step of the algebra. Hopefully you're okay. And then you would just go pull these angles from the unit circle, right? Cosine being negative 1/2, cosine's the x, negative means left, and the 1/2 doesn't go very far. And then you'd have to know that this angle is 2/3, and then this one's 4/3, right? You need to know where the angles are on the unit circle. And then cosine of x equals 5. Cosine is a restricted function. The biggest it ever gets is 1. The smallest it ever gets is -1. So this part right here doesn't have any solutions. Your answer has 2 solutions, right? For the whole question, you've got 2 answers, but they're only coming from this part, from this factor. That particular branch doesn't yield any solutions. It's important that you still write it and say no solutions, so it doesn't just look like you skipped some of the work. But if cosine is ever bigger than 1 or smaller than -1, you're not going to get any answers from that chunk. All right, so factoring was the extra little bit of algebra we had on the example E. And then before we can factor on F, you need to do a Pythagorean substitution, right? E was kind of okay because I had the same trig, right? I had a cosine squared, and then I had a cosine as the linear chunk, and then I had the constant. Here I've got the cosine squared, but I have the regular sine of x, right? You want all the trig to be the same in order to factor it. Here you're going to have to do some stuff before you can factor. You can't change the sine into cosine, right? It's not how it works. But I can deal with the quadratic trig, right? There's no trig identity that's going to let you change a cosine to a sine. It just doesn't work. Or vice versa. Can't change a sine into a cosine. But if I had a sine squared, I could change that into a 1 minus cosine squared. So I could change sine squared into stuff with cosines. And then if I have a cosine squared, I could change that into 1 minus sine squared. All right, so we can work with this one, but you have to switch the quadratic piece. The linear one tells you the trig that you need to work with. The quadratic one is the one you have to change. So I got 1 minus sine squared, right? Pythagorean substitution for that chunk right there, plus 3 sine of x equals 3. I'm going to distribute the 2. Still can't factor, because when you factor, right, everything's got to be on one side of the equation, and it's got to be equal to 0. So here, and I kind of like it when the quadratic piece is positive, right? You had a positive 2 cosine squared. Here, right now, when I leave stuff on the left, I could easily bring this 3 over and have everything on the left with the 0 on the right, but then my quadratic piece is negative. You can factor it like that, it's just mildly a little bit more difficult. So instead, I'm just going to move everything over to the right. So here I'm going to take this 2 and subtract it over, right? I'm going to make the 0 appear on the left by just adding and subtracting stuff to the right. I had the 3, I'm going to move the 2 over. 3 minus 2 is 1. This, I'm going to add it over, so I'd have a 2 sine squared. This you would need to subtract over. And then the constant. You had 3, you subtracted the 2. So now I've got it all on one side. Now I'm ready to factor, and then you'll be okay. Again, you could switch it and have 2x squared minus 3x plus 1. And if you need to factor it like that, that's fine. I believe that one would factor, 2x minus 1 and then x minus 1, I think. Let's check. That would be 2x squared. That would be a negative 2x. That would be a negative x. So negative 2, negative 1. Yep. And then the negative times the negative. Yep. So that's how it factors. But remember, you're not just working with x's. You're working with sine of x's. So this one's going to be 2 sine of x minus 1. Sine of x minus 1. That's the form for how it factors. But instead of x's, you need to go back to sine of x's. Right, so we had an extra step. The previous example you could factor right away. Here you have to do the Pythagorean substitution and a little bit of algebra before you can factor. Then you would set each chunk equal to 0. And then you need to go pull your answers from the unit circle. So sine of x equals 1/2. That's like the third time. I think that's already came up. I've already done it. So we have the pi over 6 and the 5 pi over 6. And then the sine being 1. That's only once at the very top of the unit circle. So here we ended up having 3 answers. Right? A little bit harder, right? We had to just factor on E, but on F we had to do a Pythagorean, then do some extra do some extra algebra, but then you could factor. Right? A lot of steps involved in that, but again, you don't typically see stuff that complicated, but you need to be prepared just in case. Alright, moving on to the next one. Here you're going to need to do a double angle substitution, right? You got sine of 2x and the cosine of x You don't really want to have trig with different arguments. So we're going to use the double angle to get rid of that sine of 2x. Knowing that double angle is 2 sine cosine, that's how I always remember it, plus cosine of x. So just a double angle in that first chunk. And then you see both of those have a cosine, so you can factor out that cosine. And then you set each factor equal to 0. And then you just need to go pull these angles from the unit circle. So the angles are cosine 0. Let's think about it. Cosine is 0. Cosine is the x. So there's actually 2 points on the unit circle where the x value is 0. It's up at the top. Oops, that's the wrong denominator. I was already thinking about the next one. It's pi over 2 up at the top, and then 3 pi over 2. Started writing that 3 before I finished the first one. That was dumb. Right, so those are the two answers that satisfy the cosine being 0, and then the y value being negative 1/2. That's those two angles, which is going to be the 7/6 and the 11/6. It's not too bad. Alright, and then the next one, we've got a cosine with a double angle. Now remember, from this double angle, you really have the 3 options. You could change the cosine to theta into cosine squared minus sine squared, but we know from doing the example F that you don't want to have both types of trigs. You're either going to want it all with cosines or all with sines, right? So you've got 3 different options for the cosine double angle. I could change it to this, but you're probably not going to want to. I could change it to this, or I could change it to this. Now let's go look at this example, right? This we know we're going to change to something, but if you look on the other side of the equation, I have a sine of x. So I know I need to work with sines. So out of these 3 options, this is the one that you would want to use for your double angle, right? You want to use the ones that are going to switch it into only sines. So here I'm going to change this into 1 minus 2 sine squared of x. And then again, the quadratic piece is negative, so I'm going to move stuff over, add this over, and I have 2 sine squared. That was already there, so plus sine of x, move the 1 over, and then you can factor it, and then it's just like one we did in part E. So factor it, and then you'll be ready to go. I'm not going to do stuff like this. If you need to, put it into x's before you can factor, that's fine. But I'm not going to. This one's going to be just 2 sine minus 1, and then sine of x plus 1. Always check to see if you factored it correctly, but I know this is good. Set each factor equal to 0. And then you just need to go pull those angles from the unit circle. So sine is 1/2. Sine's the y value. 1/2 is not a very big number. So it's this angle and this angle, which, it's like the 4th time that's come up. It's the 1/6, and then the 5/6, and then the sine being negative 1. That's just down there at the bottom. Okay. And then the last 2, which are a little bit more annoying because they have strange arguments, right? These 2 had weirder arguments. Like, we really like it when it's just x's inside of the trig, but whenever you have something different, you can still solve those. It's just usually going to involve a little bit more work, right? So let's go ahead and let's do this example I, and then the j, and then we'll be done with all the trig review. All right, so 2 cosine x over 2 equals the root of 3. Now, first thing you'd want to do is get the trig by itself. So divide the 2 over. And then I like to think about kind of ignoring the argument for now, right? I've got cosine of stuff. Now I'm just going to ignore what that stuff is for now. But I've got cosine of stuff. That needs to be equal to root of 3 over 2. All right, so then I'm going to go to my unit circle. Cosine of stuff is root 3 over 2, cosine's the x, and that's the bigger number. So I know there's 2 points on the unit circle, so that the cosine of that angle is root 3 over 2. Right? Really what I'm going to do is just copy this stuff for now, And then I'm going to actually pull more angles than I think I need, right? And once you kind of get good at these and you understand the logic behind these types of questions, you don't really have to write extra answers and then cross them off. But I always like to do that at least the first time. So cosine of stuff, just copied what this stuff was. Cosine of stuff is the root of 3 over 2. And then I'm going to go pull some angles. Now let's see. I'm going to use a negative angle just to demonstrate a point, but we'll just see. So negative pi over 6 would work, right? Cosine of negative pi over 6 would land you at that spot, which would give you the right cosine value. Then you have the positive pi over 6. Then if you were to go all the way around again, you have the 11/6. Let's go around one more time. I think that would be 13/6 and then 23/6. And there's infinitely many angles. If you think about cosine of what equals root 3 over 2, there's infinitely many angles that satisfy cosine of stuff equals root 3 over 2. I just pulled this list, right? I did one negative, then I went around the unit circle once, then I went around the unit circle a second time. I could keep going and keep snagging those coterminal angles, but I'm not going to, right? I'm done right now. Now, you still need to answer the question, because that's not the final answer. The final answer is to get x equals, to get the values of x. We have x over 2. So what I need to do now is go from x over 2 to just x. Well, how you undo division by 2 is you multiply. So now I'm going to take this whole list and I'm going to multiply everything by 2. So I'm going to have, if you have multiplied by 2, right, 2 over 6, that's just going to reduce to third. So this list is going to stay pretty much the same, except all of the denominators, instead of them being 6's, the denominators will be 3's. And we're thinking about how that list could still be infinitely long, but remember back to the very beginning of these examples, we only want the final answers to land between 0 and 2 pi, right? So final answers between 0 and 2 pi. Let's go see which ones we want and then which ones we don't want. Negative 1/3, that's not between 0 and 2 pi. Right? And anything else negative is also not going to work. So I found the first one that failed on the left, and then I knew everything else to the left of it was also going to fail. Let's check. 1/3, that's between 0 and 2. Ooh, 11/3. 11/3 is bigger than 2, right? 6/3 would be 2. So even if I had a 6 on the numerator, that would be too big. So that one's too big, and then since you have these in ascending order, once you find the first one that's too big, everything else is going to also be too big. So this question only ends up having the one answer, just pi over 3. You end up having some extra stuff written and then crossed out, because you play it safe, you want to make sure you have all the answers. But there was just the one final answer. All right, let's go do J, and then I'll kind of explain a little bit more about these two. All right, last one, we have sine 3x. You're going to add the root of 3 over, divide by 2. All right, it's always kind of the first step, is to get the trig by itself. And then I'm going to just copy what that stuff is. And then I've got the sine of stuff is root 3 over 2. There's 2 spots on the unit circle where sine of stuff is root 3 over 2. And then I'm just going to pull a list of angles. And then we'll figure out what the final answers need to end up being. So let's see it. Let's go get a negative angle. I think that would end up being, let's see, that would be 1/3, 2/3, 3/3. So a negative 4/3 would work. Negative 4/3 would land you on this point. Okay, and then let's see, we got 1/3 and 2/3. That's my set of answers for right now from going around the unit circle once. Let's go around again, right? So add 2 pi. 2 pi would be the same thing as 6/3. So 1/3 plus 6/3 would be 7/3. So 7/3 and 8/3 would be the answers right now from the second revolution. Let's go around one more time. So 7 plus 6 would be 13. Oh my gosh, come on, I'm running out of room. 13 and 14. Okay, I'm going to erase this and rewrite it just a little bit nicer so I'm not running off the page. Sorry, I really should have planned that a little bit better, but that's okay. So we had the negative 4/3, then we had the 1/3. Oh, I'm off the screen. Sorry. Then we had the 2/3, Then we had 7, oops, not 7 over 8, 7 thirds, and then 8 thirds, and then we had 13 and 14. Oops, here I go again, trying to write the 14 on the bottom. Now, I'm going to do one more revolution, just to try to make a point, right? So I'm going to add another 6 to the top, so I'd have 19, I'll stop there, I only did the one. The next one would be 20 thirds, and then so on and so forth. So I've got this list, and I know that list would keep going. There's infinitely many answers that satisfy sine of stuff equals root 3 over 2, right? And I always like to put in the extra work at the beginning to make sure I have all of the answers at the end. Now, we're still not done. There's a couple more things to do. Instead of 3x, we just want x. So you'd have to divide everything by 3. And when you divide by 3's, instead of these denominator being 3, when you divide, you're going to stick another 3 in the denominator. So instead of them all being 3's on the bottom, they're now all going to be 9's in the bottom. So I could have negative 4 ninths, 1 ninth, 2 ninths, 7 ninths, 8 ninths, 13, 14, and 19. You have more, right? 20 ninths would be another one that looks okay, so on and so forth. So I've got this list. We did all the work to get the x equals, and I have this really long list, and we only want the ones that are between 0 and 2 pi. So let's go through and think about which answers we want. Negative is not between 0 and 2 pi, so that one's not going to work. And any other negative angle would also not work. That's why you really don't have to write the negative angle, right? Because when you get rid of this 3, dividing by 3 isn't going to magically fix the issue, right? The thing that's negative stayed negative. It doesn't magically move to land between 0 and 2, right? So you don't have to write the negatives. I usually like to, because I like to visually see, hey, this answer is the first one that fails on the left. That's the first one that's too small, and then everything else to the left of it would also be too small. But then 1 ninth is fine, right? We're looking for the answers between 0 and 2. 2 would be the same thing as 18 ninths. So we're looking for between 0 and 18 ninths. Well, 1 ninth is going to work. 2 ninths, that's fine. 7 is fine. 8 ninths, right? That's less than 1. 13 ninths is fine. 14 ninths is fine. What about 19 ninths? 19 is bigger than 18, so that angle right there is bigger than 2 pi, so you don't need it. And then you would also not need the 20. You wouldn't need anything else past it, right? So we have just the 6 answers, right? You had these 2, which came from this, which were the set from the first trip around the unit circle. You had these 2, the 7 and the 8, that was going around the unit circle the second time. And then you had these 2, which was coming from the third set around the unit circle. Didn't need the 4th revolution set of coterminal angles because they were too big, right? You only want the finals between 0 and 2 pi. Now, let's think about something really quickly. Like why do I go through and do all this extra work, or how could I potentially skip some of this extra work? We know that we want the final answers to be between 0 and 2, right? This is the land where we want to live. We're okay with the 0. We don't really want the 2, right? Let's look at the algebra that we had to do. On the example I, the very final step was to multiply by 2, right? That's how I got rid of this algebra. I knew I had x over 2, so the very last thing I'm going to have to do is multiply by 2. Whereas on the example J, I knew to get from the 3x to the x, I was going to have to divide by 3. So you can kind of look at the argument inside of the trig, and you know what the last step of the algebra is. It's either going to be multiply by something or divide by something. So let's think about a little bit of a conceptual idea. If I divide by 2, that's going to make something smaller, right? Actually, I multiplied by 2, I divided by 3. So let's go divide by 3, sorry. When I divide by 3, you're going to make something smaller. If I multiply by 2, you make something larger, right? Division makes something smaller, multiplication makes something larger. So let's think about something. If I had an angle like this, let's say it was like 1.8. If I took 1.8, which initially falls in my interval, right? It is initially between 0 and 2. If I were to take this, and if I were to multiply by 2, right, you would get 3.6. So you would start off with something that was between 0 and 2, but when you make it bigger by a scale factor of 2, it starts off inside, but then it ends up being too big. Right? So sometimes when you know your last step, oh, I'm about to sneeze, I think. Sometimes when you know your last step, sorry, I totally did sneeze, but at least I managed to pause it. All right, so when you know your last step is going to be to multiply something, right? This guy right here, the 11/6, that one started in my interval, but when I multiplied by 2, I made it too big, right? This started between 0 and 2 pi, but then when I doubled it, it was too big, right? So really, I didn't even need, right? This was the set from the first revolution around the unit circle. I didn't even need both of those. This one was fine, right? 1/6, because when I double it, say well 1/6, when I double it, it still falls in that interval. Right? But some stuff, if it's kind of close to 2, when you double it, it's going to balloon up and it's going to become too big. You think about just mathematically, if you had 1, if I had 1 and I doubled it, it would land on 2. And remember, we weren't really caring about the 2, we were strictly less than the 2 pi. So really, all I wanted initially, if I was going to multiply by 2, all I really want are the things between 0 and 1. Because any of the points between 0 and 1, when you double it, would stay between 0 and 2. Anything that started off too big is still going to be too big, right? That's pretty easy. Anything that started off inside, but was between 1 and 2, when you multiply it and double it, it's going to become too big. If you want your final to be between 0 and 2, and you know what you were doing was making stuff twice as big, you really only needed the angles that started between 0 and 1. Right? So you didn't really need this whole list. You certainly didn't need the negative, because multiplying by 2 isn't going to magically make that answer land between 0 and 2. Right? Still going to be negative, still not going to want it. All this other stuff, like those started too big, and so of course they were way too big when I doubled them. This one started off okay, but then when I double it, it got pushed out of the interval. This one started small, right? It was in that 0 to 1 interval, so then even though I doubled it and it got twice as big, it still was small enough to land between 0 and 2. Right? So when you have the angle, or when you have the argument, something like x over 2, you're not going to have to go around a second or a third time. You're only going to need to go around the unit circle once. And really here, you would only need to go halfway around the unit circle. You would only need to potentially look at the angles between 0 and pi, right? So this coefficient, right, the 1/2, this 1/2 kind of tells you how far around the circle you need to go. If you had an angle right here, when you double it, it's going to land too big. Even if you had an angle right here, when you double it, it wouldn't land between 0 and 2 pi, right? So the 1/2 tells you how far around the circle. Now, it doesn't tell you just go to 0 to 1 to pi over 2. It means go halfway around the circle, so just be careful. This coefficient 1/2 means you're only really going to want the angles that take you halfway around the circle. Now, look at the last one, and then we'll be done, right? I promise, we're almost done. We have 2 sine of x, or 2 sine of 3x, right? Here, I knew the last step was going to be division by 3. Well, when you divide, you make something smaller. Remember, we want the final answers to land between 0 and 2. Well, if I have any angle that's here, right, obviously the negative stuff's not going to work. Because when you divide, it doesn't magically change it from negative and then fix it to all of a sudden being positive. The negative stuff's not going to work. So you don't really ever need to, I just kind of visually like to see it there. But if I want the final answers to be between 0 and 2, well, if I had something that started between 0 and 2, when I divide, right, you make something smaller. So if it started off in the interval, when I divide it, it's still going to be an interval, right? It gets smaller. But here's the weird thing. I could sometimes have answers, like let's say 3. If I started off with 3, and then I divided it by 3, like it would land in the interval. So some of the stuff, right, here's where we want at the end. That's where we want to land. some of the stuff that starts off too big, when you go through and you do that algebra, it shrinks it down, and then it lands in the interval where we want our answers to be. Everything that started off there was fine, and then even some of the stuff that initially looked like it was too big, when you divide it, it's going to be fine. Right? So let's think about going back to this example. The 13 thirds, that's bigger than 2 pi, right? So that looked like it wasn't going to work. But when you take this and you divide it by 3, it then fits in the interval. So you got to be careful. Sometimes you have stuff that starts off too big, but then when you divide it, it lands in the interval. So you got to watch out for those kind of creepy ones. They just sneak up on you, and they're going to get you. And here's why I like to do the extra work. If you had only gone around the unit circle once, right, you would have gotten these 2 answers, which means when you have divided by 3, you would have gotten those 2 answers, which is great, but then you're missing some. If you had gone around the unit circle only twice, that's great. You would have 4 of the 6 answers, so you would still lose points. Or if it was a multiple choice question, you'd get it all wrong, right, which is sad. You actually needed to go around 1, 2, 3 times. You needed 3 complete sets of angles, and those were all the answers that ended up being between 0 and 2 pi. And let's look back at the coefficient, 3. Right? This 3 tells you exactly how many times around the circle you're going to need to go. Just like the 1/2 told you really only needed to go halfway around the circle, everything else, when you multiply by 2, is going to become too big. Here, when you have the 3x, you're going to actually be dividing. So some stuff that starts off too big, when you divide it and you make it smaller, is going to end up being okay. Now the 19 thirds was just way too big. Even when you took this and you divided it and you made it smaller, it was still too big. So you didn't need that 4th revolution. The coefficient tells you how many times or how far around the circle you need to go. But those weirder argument ones, they're a little bit more challenging, but they're still very doable. I like to visually see the first thing that fails on the left, because then I know anything else to the left of it also isn't going to work. And even though I knew this 19 thirds wasn't going to work, right? I knew the 4th period where that first set of coterminal angles, I knew that wasn't going to end up landing where I wanted it to be. But I kind of like seeing that first answer that fails, and then I know everything else to the right of it would also be no good. Right, so I kind of like to see the entire set. If you only write out those, you may be missing some stuff. All right, but the more you do with this, the better you'll get. Hopefully it makes sense. Again, most of the trig that we see this year is going to be like this, kind of the more basic examples. You need to know your unit circle, and specifically, you need to know where the angles in radians are around the unit circle.